So we'll talk about modulation and demodulation again. This time we're going to look at modulation index and deviation ratio. Probably have to memorize those. I have trouble remembering the difference between them. A little about frequency and time division multiplexing and orthogonal frequency division multiplexing, mixing, multiplication, frequency multiplication, bandwidths on various modes, and some more on frequency deviation and duty cycle and intermodulation. So in FM, the two primary parameters are deviation ratio and modulation index. The deviation ratio is the ratio of the maximum carrier frequency deviation to the highest audio modulating frequency. So that formula, which got wrapped, is the deviation ratio is the delta of the carrier frequency deviation, or the delta is the deviation, divided by the maximum modulating frequency. So let's say you were just doing it with a 1 kilohertz tone. So your FM max would be 1 kilohertz. And you divide that into your carrier deviation, and you set that up for, let's say it's 5, I don't remember what the standard ones are, 5 or 6 megahertz deviation. So that would give you the deviation ratio. In other words, how much the frequency deviates per modulating frequency in hertz. Because it doesn't have any units because they're both hertz. But
Bob, isn't that deviation ratio a matter of both design and operator setting?
say that again?
Isn't the deviation ratio, the deviation actually, a matter of design as well as operator setting?
Yes.
So it's not something one would know a priori. It's a matter of setup of the equipment, design and setup.
Right. Normally for your FM channel, you're going to have a certain deviation, and the frequency range you're using for modulating it is going to determine that ratio. It's just, I don't know, maybe it's a figure of merit or something.
Well, I was thinking that it would be a matter of the gain applied to the varactor on the oscillator.
Well, that's how it gets affected, but it's just a measure of, the deviation per the modulating frequency.
Well, it measure the result, of course, but the amount of deviation could be from narrow to god awful wide.
Correct. So you'd have a different value of D.
Yeah.
This is just telling you how you calculate D.
Yeah, okay.
So the other one that is similar enough, it's hard to, for me at least, to remember the difference, is the modulation index, which we use beta. And it's the deviation frequency, or frequency deviation, divided by the modulating signal frequency. So they're very, very similar, except here we're using the modulating frequency. In the other one, we're using the highest modulating frequency. So I guess in one case, you're using the max deviation divided by the max modulating frequency. In this one, we're using, I guess, the average deviation divided by the average modulating frequency. Very confusing to me. You just have to remember the formulas for the exam. So an example is, if you had a phone signal with a maximum deviation of 5 kilohertz, and the maximum modulating frequency is 3 kilohertz, then your deviation ratio comes out to 1.67. Which means that your modulated FM signal varies 1.67 hertz for every hertz variation of your modulating signal. That's all that's telling you.
What's C max?
Your carrier max, and FM is the modulation frequency. So I think the basic way to remember, this is the max divided by the max.
And M max is what you said?
Modulating max. So if you speak into the microphone and your voice goes up 3 kilohertz, the carrier is going to modulate or going to change by 5 kilohertz. Is all it's saying.
Why does it change differently than what is being modulated with?
Because whoever designed it did it that way.
Well, they screwed it up.
Well, you think it should be 1-to-1?
Well, I thought so.
Well, could be. I don't think that's the case, though. I think it's normally a larger number than 1. Well, first time I ran across these, they kind of threw me too. Like, what? And why do I care? So what is the deviation ratio? No, that's a specific one. They want the general definition. I'll go with Bravo, I think. What's the deviation ratio of an FM phone signal having a maximum frequency swing of plus or minus 5 kilohertz when the maximum modulation frequency is 3 kilohertz? Here you go, Ed.
It's what we just calculated a little bit ago.
High math.
1.67. I told you had to divide today. What's the deviation ratio of a phone signal having a maximum frequency swing of plus or minus 7.5 kilohertz, and the highest modulating frequency is 3.5 kilohertz? Should be able to do that without a calculator.
2.14.
Just divide one by the other.
I know, but I'm trying to make notes and I'm missing stuff.
This calculator gave you about 16 numbers.
Yeah, calculators can mess you up.
Yeah, well, the first 3 were right.
Okay.
The rest of that back there is.
Okay. Modulation index is the other confusing one. So if we had a deviation of 3 kilohertz on either side of the carrier, so it's plus or minus 3 kilohertz. And the modulating frequency is 1 kilohertz, then the modulation index is 3, or 3,000 divided by 1,000. Pretty simple. The difference here is they're not asking for the max deviation or the max modulating frequency. But I don't know, is that the average deviation they're talking about? I don't know. It confuses me. I can remember how to answer the question on the test, but I can't say that I totally understand the point of these. And maybe if you're designing an FM system, you care a lot more. But as an operation, I don't know why I would care. I don't do much FM except for VHF, UHF, and I don't know of any adjustment to affect the deviation. Unless you go inside the radio, and Clyde has some tools to calibrate it. But as a user, yeah. As a user, there's no adjustments on most FM, VHF, UHF radios where I can adjust that I'm aware of. Right. But somebody decided it was a good test question. So what's the modulation index of an FM signal? Sorry, I hate computers. I used to design them. I don't like to use them. How does the modulation index of a phase modulated emission vary with RF carrier frequency? Who doesn't care? What's the modulation index of a phone signal having a maximum frequency deviation of 3 kilohertz either side of the carrier when the modulating frequency is 1 kilohertz?
3. 3.
What's the modulation index of an FM phone signal having a maximum carrier deviation of plus or minus 6 kilohertz if the highest modulating frequency is 2 kilohertz? There was 2 of those, so odds are twice as good you get one. Frequency and time division multiplexing. Essentially 2 types, either frequency or time. In the case of frequency, you're going to take 1 or 2 or more baseband signals and modulate the transmitter or the carrier and get information at different frequencies. That's the way essentially broadband cable works, where they put all the TV channels on there, and they're all at different space at different frequencies. That's frequency division multiplexing. So they may have I don't know, how many TV channels used to do on cable? 500 or something.
A whole bunch. They're both of them.
Whereas time division multiplexing, you basically sample those signals and transmit them in different time slots. So you'll transmit one part of one baseband signal, then another one, and possibly another one, depending on how many you have. And then kind of round robin that thing. And do it fast enough that on the other end, when you're taking them apart, you put it back together and people don't know the difference. That's one of the things that's supposedly a great feature on DMR is that it uses two time slots, can use two time slots. So you can have two signals going on at the same time. I've never seen that in operation, but that's always touted as one of the features that it has that D-Star and Fusion don't. So in the case of frequency division, you basically have divided up that total bandwidth into what they call non-overlapping frequency bands. So you have all these essentially channels that you're converting the baseband signals into. They do the same thing on fiber. Your TV channels coming in on fiber or your internet. It's the same kind of way. So what is frequency division multiplexing? I guess this is supposed to be time. Oh, orthogonal. Okay. In this one, you have multiple basebands used to modulate more than one carrier. So you can have, and I think the carrier this might be like an I and Q because it's orthogonal. So I think they're maybe 90 degrees apart. So you modulate those just like you would do for generating an I and Q signal on a radio. So each one's going to have a different amplitude and phase. What is digital time division multiplexing? We talked about that a little bit. So it's different time slots instead of different frequencies. Honestly, I don't know a whole lot about this one. But apparently that's what DSL uses. Maybe that's why DSL so orthogonal frequency division multiplexing. If you have AT&T non-fiber internet, you're using DSL over your telephone copper pair. That's what it says. Must be true.
5G is faster
Then what?
than DSL.
Oh, yeah. I mean, DSL is limited by other physical means, basically because it's on the copper pair. 4G and 5G are wireless, much wider, much higher frequency. Because that's what, 2.4 or 5 gigahertz. DSL is not anywhere near that. And apparently they also use it on power line networks. I don't remember what they used to use. When I was in college, I worked for the power company, and the controls for all of the substation equipment and stuff was done over the power line, but I don't know what protocol they used. Orthogonal frequency division multiplexing technique used for which type of amateur communications? What describes orthogonal frequency division multiplexing? If all else fails, go for the longest description.
It's good strategy.
Big words, bigger words.
On a lot of these, the main thing is to remember a few key words that make it different than the others. In this case, inner symbol. It's one thing that's unique about it.
So you're interested.
Okay, frequency mixing. And here we got our old sum and difference, because we're actually multiplying two frequencies together. And when we do that, you wind up with the sum and difference and actually the other two signals, the original two signals plus the sum and difference of them. And that's why it's different in a balanced mixer. It eliminates a couple of those components like the carrier. So all you get is the sum and difference if it's a balanced mixer. When they first started doing that, that's where the term heterodyning came from, where they were mixing your RF signal with your local oscillator. Little pictures are showing what happens in what they call a down conversion versus an up conversion. In the down conversion, we have our RF signal coming into the mixer and the local oscillator, and we're going to get out an intermediate frequency, which in most cases is going to be a lower frequency than the RF coming in, so that you can operate on it easier. Wouldn't make a lot of sense to make it higher. So typically, like in old radios, that would be like a 10.7 megahertz, or I think maybe they used 9s and 5s, and eventually down to 455 kilohertz was a typical AM radio. So you wind up with the IF down here, and the original RF and local oscillator frequencies are up here.
So the local oscillator frequency is higher than the received frequency.
Yeah. And then, they're so far away, it's easy to get rid of that if you need to get rid of it, because in your IF amplifier strip, you're only you only care about amplifying this passband. In the case of the up conversion, it's where you're transmitting. You've generated an intermediate frequency and you're mixing it again with a local oscillator to get it up to the transmit frequency. And what you get out is your RF or your modulated carrier. So the IF is down here, the local oscillator is here, so you get your sum and differences at this point. So what's another term for mixing of two RF signals? What combination of a mixer's local oscillator and RF input frequencies is found in the output? Sum and difference. Let's see. And this is just kind of showing the case where you got a bunch of RF stations out there fairly close together, all the little different colors. And your local oscillator frequency down here. This is obviously AM radio, 1.4 megahertz. All of these are coming into the receiver and they're getting mixed with the local oscillator. So you're going to see all of these output of the mixture. Okay. And your IF passband is down here at 455 kilohertz. So ideally, you're only going to see the green one, assuming that your IF bandpass filter is good enough. The wider that is, the more of these adjacent signals you're going to see. And if I change the frequency of the local oscillator, then I can pick any one of these 5 by shifting it to where they are. Okay. Which mixture input is varied or tuned to convert signals of different frequencies to an intermediate frequency? Usually, I think nowadays they tend to call it a VFO as opposed to local oscillator. Because back in the day, the local oscillator was fixed because it was a crystal you plugged in.
That's so signal.
Huh?
I was like plugging it in.
Change crystals or have a switch.
Oh, wow. My first fancy VHF radio had like 60 crystals in it.
Okay, image response. So if you tune in a signal, okay, you can have another signal that is twice the IF distance away. And you'll receive it also. And it's called an image response. And that's what this chart is kind of trying to show, where the image shows up. The example there, you got a 13.8 megahertz VFO. You're receiving a 14.255 megahertz signal. So the difference between those supposedly is 455 kilohertz. That looks about right. But if you had another signal at 13.345, it would also mix and generate a 455 IF signal. So if you don't have a very selective front end, you're going to get those two signals, one on top of another.
How's that inflicted on that chart? Mine's low. All low.
Low is your BFO.
Well, here's the local oscillator. Here's the RF signal. Okay. Here's the image. Okay, because we're trying to receive 14.255, which would be this one. But we have one at 13.345, which is down here. It's lower on the other side of the local oscillator. So they're both going to give you the same IF frequency, 455. And then you got all these harmonics and other products floating around. But like I said, they seem to have dropped the hard question about that part of it. So what's the term for interference from a signal at twice the IF frequency from the desired signal? Okay. Now instead of mixing, we're going to multiply, which normally is what you do in FM or transmission, because you will generate your modulated signal at a lower frequency and then use a frequency multiplier to get it up to your desired output frequency. And you do that with an amplifier, and they call them in the FM world doublers and triplers. It's just an amplifier that's tuned to a second or third harmonic. So you feed in the fundamental and it amplifies the harmonic of it. And they usually don't go more than 2 or 3, but you can stack them. So if you want 4, you put 2 doublers together and multiply the frequency up by 4. And that does also change the deviation.
An amplifier that amplifies the harmonic. What's it do to the fundamental?
Transmitter fundamental frequency.
You filter it out.
I don't know. I never built one. I don't know.
Well, you would have to, I would think, if you'd have an amplifier, a multiplier,
Mm-hmm.
and it amplifies the fundamental and.
Because it's tuned.
first harmonic.
It depends on the width, on the bandwidth of the tuned circuit. But you've got it tuned for the second harmonic for it to double the
Yeah,
frequency.
that's what I was getting at, so.
The fundamental
Out the
is
fundamental.
hopefully outside the pass band for that tuned circuit. Would depend on what the Q is, but because what you really want out is only the second, and you don't want the fourth either.
Have to be some really sharp filters in those amplifiers.
I suppose.
And each one would have to be different. Right?
Yeah.
Some kind of complicated.
Well, and in most FM, you're kind of fixed channels. It's not like you got a very wide, at least for broadcast FM channels. Now, I've never done FM on HF. So I guess that would be a little different. I don't know.
I'm just thinking about the actual, what do you call it, doubler or
Doubler and tripler.
to build the doubler. The first doubler is gonna take whatever you're starting out with.
And double
it's
it.
gonna
Double the
double it.
frequency.
And you're gonna filter out the fundamental.
And harmonics.
And harmonics above the second harmonic.
All right.
So it's gonna be a very narrow filter. And then you're gonna do that again.
Well, it isn't necessarily a filter, it's a tuned circuit. So it depends on the Q of the circuit as to
Well,
what the bandwidth is going to be. But yeah, it
Yeah.
kind of acts like a bandpass filter.
Yeah, you're making a very high Q bandpass filter.
Yeah. Yep. And it could be a Class C amplifier. Probably is. That's one of the few places you can use one is FM. Because you don't care about the amplitude.
Well,
Did we beat that one to death? Okay. What's the stage in a VHF, UHF, FM transmitter that generates a harmonic of a lower frequency signal to reach the desired operating frequency? Sure it's not a reactance modulator?
sounds good.
Although I don't know what a balanced converter is. Never heard of that one. Okay, talk a little about bandwidth. Okay, if we talked about things like FT8, which is 50 hertz wide, Pactor, which is an old one, but I guess it's still around. Can't say I've ever done that. That's the one that requires the proprietary modem, I believe. So it wasn't freebie. It's 2300 hertz. And standard FM phone with a 5 kilohertz deviation and our 3 kilohertz modulating frequency has a 16 kilohertz bandwidth. For some reason, I was thinking that FM bandwidth was more like 12 to 15. Must be right. It says so right there. What's the relationship between transmitted symbol rate and bandwidth? Well, the higher the symbol rate, the wider the bandwidth.
Is that because your symbols get larger?
No, not necessarily. It's just the rate at which they're changing. Signal to noise. Digital modes seem to be much more susceptible to noise than AM. In a digital mode, if it gets too noisy, you just lose the signal. And AM or single sideband, if you got noise, you might still be able to understand what's going on. But digital is digital. You either get a nice signal or you don't. And one of the things you want to do in either case is match the bandwidth that you're using. And you usually have selectable IF filters. In a lot of radios, they automatically change depending on what mode you're in. Like if you switch to CW, it'll switch in a very narrow filter. If you switch in AM, you get the widest filter. If you're single sideband, you get like filter 2, which is like 3 kilohertz or whatever. And the reason you do that is it gives you the best signal to noise ratio. Since the signal to noise ratio is the ratio of the signal to the noise power within the band. So the narrower the band that you're receiving, the less noise power. So ideally, well, I guess you can actually do it. Like on FT8, if you really wanted to key in on a particular station, you could narrow it down to, a little over 50 hertz centered on that guy. And, get the best, improve your signal noise ratio for somebody that's over there in Maldives, weird place.
So it makes it a little easier on the conversion.
Yeah, you don't have all those other channels either.
You know, they're changing the bandwidth of FTA from 3 kilohertz to 40 kilohertz.
What? Who?
It's upcoming. I swear,
3 to 40?
40, and it's a 13x improvement in the bandwidth for FTA.
Yeah, but what's it gonna take to be able to decode?
Well, yeah, that's the problem, that it's not gonna run away because you'll need a supercomputer to process it. Yeah.
So the formula for signal to noise ratio is the power of the signal divided by the power of the noise. Now, I always thought it was the signal plus the noise divided by the noise. Or the other way around, but
That wouldn't be a ratio, it'd be like.
no, you divide one by the other. But this must be right, because it was on the internet.
So how do you get the power of the signal without the noise added into it? How do you get the numbers?
That's a good question.
Just buy one of them newfangled magic receivers.
All of that magic receiver.
Now, that one I built displays the dBm of the received signal.
Including the noise.
No.
How does it know the filter out?
Well, it only includes the noise within the passband, as opposed to the noise floor. Because noise floor was down around 130, 140 dBm, excuse me.
Well,
So why is it good to match receiver bandwidth to bandwidth of the operating mode?
Gee, David.
Very good.
that's power you receive.
Okay. Frequency deviation, which is delta F, that came up in the previous formula for the peak frequency deviation of the signal. And we use that delta FC for the peak deviation of the carrier and delta FM for the peak deviation of the modulating signal. And did that deviation ratio. I'm just showing another example there with for a 5 kilohertz deviation and the carrier of 146.52, then in a modulating frequency of 12.2 megahertz, and you get that delta FM, work it out to 416.7 hertz. I forgot why that's there, but I'm sure I'll remember it on the next slide. I think I was just trying to put down what all those things that we talked about. But it does come up here in this thing called Carson's bandwidth rule, which is a way to estimate what the bandwidth is for a signal. So it's 2 times the deviation, the delta F, the deviation, plus the modulating frequency. So if you had a 5 kilohertz deviation and a 3 kilohertz modulation frequency, then that adds up to 8 multiplied by 2 gives you the 16 kilohertz bandwidth for a typical FM signal at that with those numbers. I guess you could use that formula for FT8. Be interesting to see if you came up with 50 hertz.
Yeah.
6.25. 6.25 hertz is the deviation for FT8.
You just happen to know.
Yeah, 50 divided by 8.
Oh, okay, all right, that's.
But then I don't know what the modulating frequency is. There's a digital, it probably doesn't apply to this. So what's the frequency deviation for a 12.21 megahertz reactance modulated oscillator in a 5 kilohertz deviation, 146.52 megahertz FM phone transmitter?
Probably. Oh. So that is an actual question. Oh, that's a term.
Yeah. Generals get the hard one.
I must have passed that at some time or another.
Maybe not. How long ago was it?
11 years.
Probably wasn't on there. They change every 4 years. What's the total bandwidth of an FM phone transmission having 5 kilohertz deviation and 3 kilohertz modulating frequency? Remember 5 plus 3 times 2. Duty cycle. It's defined as the fraction of one period in which a signal or system is active. I always thought it was just the percentage of transmit time per unit time. And the formula there, D time on divided by the total time. Yes? And the nice little animated graph there is showing you what the waveform looks like at different duty cycles. The one, I think the reason they bring it up is for things like FT8 and for instance, I guess FT4 is the same. They're both running at 50% duty cycle. So most modes like single sideband, FM, AM are nowhere near 50% duty cycle. So you could have, well, in fact, I have an antenna that can't handle 100 watts at 50% duty cycle for a long period of time because of the ferrite cores and the feed and the matching. They heat up and you actually see your SWR changing. And
When you set up a beacon and whisper, you can specify the duty cycle. How much you're going to do.
so why is it important to know the duty cycle of the mode you are using when transmitting? The other reason that'll come up in safety, which I guess would be the last week, on exposure calculations. And that's one of the parameters, the duty cycle. Has everybody updated their exposure calculations when you made any changes?
It's about.
You didn't change antennas or anything,
My
right?
story.
Okay, intermodulation. That's where you're getting two signals combining or being mixed, okay, in some nonlinear circuit, which is actually what a mixer is. But it could be, like we talked about before, a rusty bolt makes a nonlinear, almost like a diode. So that's where you get these products. And the first odd order, which would be the third, is 2F1 minus F2 and 2F2 minus F1. And it turns out that those particular products wind up very close frequency-wise to your F1 and F2 signals. So they're kind of hard to filter out. And this is kind of what this is showing, where your desired channels over here and you get these two interfering signals. And if something is there to mix them, then these products, you can get one over here where you don't want it. It's not unusual for that to be happening with a repeater. If you've got a rusty bolt, bad connection, something like that close by.
I had a water fountain getting you.
We have, in fact, I guess still have that problem on one of the Indian River repeaters. Managed to fix it by temporarily, because it requires a tower climb to actually find it and fix it, of changing the output tone. So it doesn't kind of match it. No. Yeah, let's go with alpha. Which intermodulation products are closest to the original signal frequencies?
Second.
Even. Even order.
Well, we got a lot of guesses.
Power order.
First order, odd order. Which of the following is an odd order intermodulation product of frequency F1 and F2? Charlie. Can be 2F1 minus F2 or 2F2 minus F1. Okay, so we talked about these very confusing deviation ratio and modulation index, which the only way I can kind of remember the difference is, in one case, it's the max deviation and frequency versus I guess these are they just don't call it max, so I'm still confused with them. Frequency division multiplexing is getting 2 or more signals modulating a carrier at different output frequencies. In time division, we have the 2 signals sharing different time slots. In orthogonal, you have 2 or more signals modulating multiple carriers, and I think they're supposed to be orthogonal. The one thing they did say about them was they were, oh gosh, terrible. Forget things. What was that term they used for the subcarriers? It wasn't part of the question, but. And then frequency mixing is the sum and difference frequencies. Image response is interference from a signal at twice the IF frequency. So it really is an indication of how good a front end filter you have on your radio. Well, no, because after the first mixer, they're both at the same IF. You can't filter it. You got to filter it before the mixer. As I recall, the 7300, for instance, has bandpass filters ahead of the mixer. They get switched in, but they're kind of broad. And Yaesu uses their roofing filter, same kind of deal, just a fancy different name. We talked about the bandwidths of FT8 and PACTOR and FM, the frequency deviation. You want to match the bandwidth with the mode, Carson's rule, duty cycle, intermodulation. Duty cycle was time on divided by total time, which gives you the percentage of transmit time, basically. And remember, for intermodulation, it's 2F1 minus F2 or 2F2 minus F1.